All right, now let's work through some example problems looking at correlation and hypothesis testing with correlation, specifically with Pearson's correlation coefficient or Pearson's R value. Remember, we're only going to look at that one type of correlation. Okay, so here is an example of a study when a researcher wants to examine the relationship between marital satisfaction and overtime hours. So you saw this in one of the example problem, or not the example problems, but one of the examples of where, maybe marital satisfaction leads to overtime or overtime leads to marital satisfaction. For our purposes, we were assuming that overtime hours is the independent variable here. So we're labeling that X, and we think that marital satisfaction is our dependent variable. It depends on overtime hours. And just to put things into context, marriage satisfaction was rated on a scale of 1 to 10. So 1 being not at all satisfied, 10 being extremely satisfied, and overtime hours, of course, would just be measured by number of hours. And then the data are right here, and we're wanting to see if there's a significant relationship between marital satisfaction and overtime hours, and if so, what is the size of the effect? And remember, to find the effect size in correlation, you simply take what you calculated, your R, and you square it. Pretty simple. All right, so let's go ahead and state our hypothesis. So for step 1, we are going to state our null and alternative hypothesis. Now, I'm going to go ahead and start with my alternative hypothesis. And I need to figure out if I have a 1 or a 2-tailed test. And if I have a 1-tailed test, if I'm expecting a positive or negative relationship. So I'm just looking, do the data indicate a significant relationship? I'm not being specific here if I think that as marital satisfaction increases, over time will tend to increase or decrease. I'm not saying I'm expecting a positive or negative relationship, just a relationship. So this is a 2-tailed test. So under the alternative hypothesis, the population correlation is just going to be something other than 0. There's some sort of relationship. So under the null, there really is no relationship, so the population correlation would be 0. Step 2. Finding R crit. The critical value of R. So I already know that my alpha level is 0.05. That's just given to me. I know that my test is a 2-tailed test. So I'm going to kind of jot down some notes to make it easier to find our crit. And then I need to know what my degrees of freedom is, which is equal to n minus 2. And we have, let's see, 1, 2, 3, 4, 5 people in our study. And 5 minus 2 is 3. That is our degrees of freedom. So now let's look at the table with the degrees of freedom of 3, 2-tailed test, alpha level 0.05. What is the minimum value that our test statistic needs to be to reject the null and say it's significant and do a happy dance? All right, 3 is our degrees of freedom. Alpha level is 0.05, 2-tailed test. So this is the only column we're interested in. The row we're interested in is degrees of freedom 3, and those two meet up at a critical value of 0.878. Now be careful, because we are doing a 2-tailed test. So it's not just 0.878, it's positive or negative 0.878. And I'm going to go ahead and draw my critical region here, or my region of rejection. So this would be my distribution. Now, instead of saying, oh, we're going to have a sample mean, our population mean is right in the middle, or our mean difference of 0 is right in the middle. Now what goes right in the middle is a correlation of 0, no relationship. And as your correlation value gets further away from this 0, be it on the negative end or the positive end, you have a stronger relationship. So don't get this confused with the scatter plot. This represents the distribution of all of the possible values for the correlation that you could get. So this represents the frequency. And remember, this distribution represents the null hypothesis, just like it always has when we're plotting critical values, whereas before we were looking at sampling distributions. Now we're looking at the distribution for the correlation. So the middle right here, this 0, under the null hypothesis, most correlations are going to be 0 because the null is saying there's no relationship. So that's why that's at the highest frequency point of the distribution. And then as you get, again, farther out in the tail, you have a stronger relationship. And remember, you're never going to have a correlation value that exceeds 1. So the extreme low end, the lowest you can have is a -1, and the highest you can have is a +1. And we are looking at the extreme 5% of this distribution split up into 2 tails. So I'm going to go ahead and shade in 2 tails here. And on the left side, I have my negative version of the critical value, 0.878. And on the right side, I have the positive version of my critical value, 0.878. And just to kind of keep things straight, we know that if our correlation coefficient falls in our critical values, we can reject the null hypothesis. And if it does not, then we're big old failures. What we expected to happen is not true, and we would fail to reject the null hypothesis and not do a happy dance. Okay, let's go ahead and do step 3 and see what our decision and conclusion should be. So I did all the preliminary calculations in this table. In the next example, I'm going to ask that you try this on your own, and I don't give you all the preliminary calculations, so I'll walk through all of this. But if you look at the formulas for the correlation, so let's go ahead and start off, say, okay, we know we're looking for a correlation, so we know we're looking for R. And R is equal to the sum of products, the covariability of x and y, divided by the square root of the sum of squares x times the sum of squares y. And I'm looking at this formula and I'm like, oh boy, I need to write down 3 formulas, right? I need to write down the formula for my numerator, the sum of products, and then my 2 sum of squares values in the denominator. All right, so the formula for the sum of products, the numerator of R, the covariability of x and y, is equal to the sum of x times y minus the sum of x times the sum of y, divided by the sample size. And then my sum of squares formula. So my sum of squares for x, that little subscript just represents that that's the sum of squares for x. So the sum of x squared minus the sum of x quantity squared. See, you thought you were getting away from sum of squares, but it's back in a big way. Sum of squares y. It's just such a useful measure of variability. So now we just replace x with y values in this formula. Sum of y squared. All right. We've got all of our formulas written down. Okay, so we've got the sum of products. Let's start there. And now you'll see why these preliminary calculations are important, right? Because for the sum of x times y, I took the sum of each x times its respective y for each person. So 4 times 8, 4 times 9, 16 times 4, 8 times 6, and 24 times 2. I even color-coded. You see it all right there. Find those values, add those together, and that gives you the first value in your sum of products. Each x times each y added together, 228. Then for the second piece here, we take the sum of x and multiply by the sum of y. So add all the x's together, then add all the y's together and take those 2 values and multiply. So I added all my x's, I added all my y's, and I have 56 times 29 here. So 56 times 29. And then I'm dividing by the total number of scores. 1, 2, 3, 4, 5. Well, not number of scores, sorry, number of people in my data set, and there's 5 people in my data set. We measured each person on overtime hours and marital satisfaction. So this becomes 228 minus, well, 56 times 29 gives me 1,624. So 1,624 divided by my sample size. So this becomes 228 minus, well, 1,624 divided by 5 is 324.8. And I end up with the sum of products of negative 96.8. Negative 96.8 is my sum of products. I'm going to put a little underline there. Negative 96.8. So real quick, I want to point out that the variability is never going to be a negative number. You're never going to have a negative number for sum of squares x or sum of squares y. What determines whether or not your correlation is negative is your sum of products. So you can get a negative sum of products, and if you do, the overall correlation will be negative. And if you get a positive, your overall correlation will be positive. And based on my scatter plot up here, I am expecting a negative relationship because I see a downward slope, right? As overtime hours increases, marital satisfaction decreases, right? Higher values here, lower values here. Lower values here, higher values here, downward slope. So I'm feeling pretty good about my calculations so far because I would expect to get a negative sum of products because I'm going to have a negative correlation because that's what it looks like in my scatter plot. Okay, now let's find the sum of squares for overtime hours, or our x variable here. Okay, so we have the sum of x squared right here. All the x's squared and added together, right? So we've got 928 minus the sum of x in parentheses, so it comes first, or 56, right up here, squared, divided by the sample size of 5. So this becomes 928 minus, well, 56 squared is 3,136. Divide that by 5. So this becomes 928 minus, so 3,136 divided by 5 is 627.2. And you have a sum of squared x of 300.8. So 300.8. Sum of squared x. So I'm going to go ahead and plug that in to my formula for my correlation. So 300.8. All right, now we need to find the sum of squares for y. So we're going to take the sum of all the y's squared and added together, right? So all the y's squared and added together gave us 201 minus the sum of y, 29 squared, divided by the sample size of 5. So this becomes 201 minus, well, 29 squared gives me 841. We're going to divide that by 5. 201 minus, so 841 divided by 5 gives me 168.2. And I end up with the sum of squares y of 32.8. It's always nice to rewrite what you found right next to the values so that it's easy to go and plug it into the formula that you need eventually. So now we have everything that we need to solve for our correlation coefficient. So the first thing we're going to do is we're going to multiply the two values in our denominator. So I'm just going to rewrite negative 96.8. Keep my square root. Don't forget to keep that square root. If you forget that step, it's going to mess you up. And then I take 300.8 times 32.8, and I get 9,866.24. So 9,866.24. Now the next step is I'm going to take the square root of that number. So negative 96.8 stays the same. And the square root of 9,866.24 is 99.329. Now I can just divide and I have my R, or my correlation coefficient, of negative 0.975. That would be my final answer for step 3. So this is all step 3, calculating your test statistic. And guess what? Just like the picture told me, I have a strong negative relationship. The downward slope tells me it's negative, and the fact that the dots come almost perfectly form a straight line tells me that it's a very strong relationship, and I'm feeling super confident about my calculations. Now when we go back, let's do step 4 here, and I'm going to go ahead and type it in. So let's see. Put that down here. All right. So I know that my value, my correlation coefficient of negative 0.975 is right here, right? It falls in the rejection region. So my decision is going to be to reject the null hypothesis. Whoa, There we go. And I'm going to conclude, remember we need to include the independent variable, the dependent variable, and the word significant. And because this is a two-tailed test, we're just going to say significant relationship, not positive or negative relationship, just relationship. So results suggest there's a significant relationship between marital satisfaction and overtime. So results suggest there is a significant relationship between, oh, I'm on a roll here. All right. Marital why can't I type? There we go. Marital satisfaction and overtime. And let's make that nice and big on the screen so you can see it real well. So again, our calculated R value, negative 0.975, falls in that critical region. So we reject the null hypothesis and say that there is a significant relationship between marital satisfaction and overtime hours. Now, because we found a significant effect, I want to know what is the size of this effect. So let's see if we have room here. Not really. We'll calculate R squared here. All right. So R squared. We simply just take the value for the correlation coefficient that we calculated, not our crit, but the one we actually calculated, and square it. So for effect size, we take R and square it. Remember, R was negative 0.975, so negative 0.975 squared. Now remember, a negative times a negative is always a positive. And some calculators get kind of screwy with that. So I would just, whenever you're squaring something, just ignore the negatives completely because the final value will be positive anyway. So negative 0.975 times negative 0.975, or negative 0.975 squared, gives you 0.951. That is a very large effect to go along with our very strong correlation. Now let me interpret what that tells you. So I'm going to get rid of this little guy and replace it with the interpretation of R squared. So if we turn this 0.951, right now it's a proportion. Let's turn it into a percent by multiplying it by 100. So we could say 95.1%. Ooh, let's make this bigger. So 95.1% of differences, let's not use the word variability because differences is a little less fancy, in marital satisfaction, our dependent variable, is predicted by the relationship between marital satisfaction and overtime hours. If we drew this as like a pie chart, because I like to think of R squared as a pie chart because this would represent all the differences in our supposed dependent variable marital satisfaction. Almost the entire pie, like all but this little teeny chunk, is predicted by our independent variable here. Now this can be kind of problematic because we don't know what the independent variable and dependent variable is. So maybe it's, the other way around. Maybe it's the marital satisfaction predicting overtime hours. But regardless, we know we have a really large effect size. Now, when we get into, partial correlations or something called multiple regression, we start to plug in more than just two variables, and we start to see R squared decreasing as more variables are entered into the equation that overlap with the other variables you're looking at. That's a little bit beyond the scope of this class, though, just a little bit. Okay, so now let's go ahead and give this one a shot. So here's the summary of the study. So Christine is an IO psychologist, wants to study relationship between workplace aggression and basically perceptions of how effective you are on the job. The fancy word for that is self-efficacy, so like your confidence in your abilities at work. She thinks that more workplace aggression tends to be related to significantly lower levels of self-efficacy, And here are the survey questions that she used to assess workplace aggression and self-efficacy. This is just to give you context of sometimes how things are measured. In reality, with survey studies, we often use very similar items measuring one single construct. So instead of just having one item measuring self-efficacy and one item measuring workplace aggression, we would have several items. But just to keep it simple, here's 2 items. Here's how it was quantitatively measured, right, on a scale of 1 to 6. This isn't as important. It's just giving you context. What's really important is looking at this data to figure out if the data suggests that people who have more workplace psychological aggression tend to have significantly lower levels of self-efficacy, and then if so, what is the size of the effect? So pause this video. I really strongly encourage you to try to do this on your own and see how well you do. Because just sitting there and passively listening to me lecture about this stuff isn't really going to help you know what you know. So let's pause it, give it a shot, and then we'll go over the answers. So let's go ahead and work through this problem. So first we want to state our hypothesis. And in this case, we actually have a one-tailed test. Now it doesn't say, does Christine expect a negative correlation? You have to be able to identify that she's expecting a negative correlation because she thinks that more workplace psychological aggression experiences will have significantly lower levels of self-efficacy, right? More workplace aggression, more X, thinking it's going to be rated to lower levels of Y. So this is a negative correlation. So for our null and our alternative hypothesis in step 1, we need to reflect that fact. So under the alternative, we think that the correlation in the population is negative or less than 0. And if it's not less than 0 under the null, which is everything else, it's either a positive correlation or it's just no correlation at all. It's equal to 0. Remember, 0 being no correlation. If you calculate R and you get 0, there's just no relationship at all. Step 2, finding R crit when you have a situation with alpha level is 0.05. That's right here. Let's see, one-tailed test. And I'm just going to go ahead and write a negative right here, right now, so I don't forget it, because I know I'm expecting a negative relationship. And my degrees of freedom, n minus 2, is equal to, let's see, 1, 2, 3, 4, 5, 6, 7. Minus 2 is 5. All right, let's look at our table here. 5 is my degrees of freedom. One-tailed test, alpha level 0.05, so I'm looking at the first column, and then here 5.669 is my critical value. So not only 0.669, but negative 0.669. So if I draw my critical region here, my frequencies, my value for R, 0 would be in the middle. And then my critical region, or my region of rejection, would be right here. And it's set by a cutoff of 0.669. So if what I calculate in step 3 falls here, we can reject the null. If not, we are failures. And we fail to reject the null. Okay, now before I do step 3, I'm going to go ahead and sketch the scatter plot for this data, just to get kind of an idea of what I think my data looks like so that I can test it against what I calculate to make sure I didn't make any mistakes. So I'm going to go ahead and draw my axes here. Remember, label your axes. So along the x-axis, we are looking at levels of aggression. Along the y-axis, we're looking at self-efficacy. And let's plot our numbers. So what makes sense? So aggression ranges from 1 to 5. So I'm going to go ahead and go from 1 to 5 in order. So 1, 2, 3, 4, 5. If we measured aggression on a scale of 1 to 100 and we had values ranging from 1 to 100, you could go, you could count by 10s or 5s, whatever makes sense, just to keep it simple but still visually see your data. Same thing for self-efficacy. It ranges from 1 to 6, so I'm just going to represent all those values here. So 0, 1, 2. Well, let's not include the 0 because we don't even have a 0 in our data set. 1, 2, 3, 4, 5, and 6. All right, now we're ready to find our dots. So 5 and 2. So 5 is right here along the x-axis, and then go up to 2. That's that first person in our data set. Then we need to find 1 along the x-axis, and go up to 5, right here. 2 to 3, so 2 along the x-axis up to 3, right here. 4 and then 1, so 4 aggression, 1 self-efficacy, right there. 6 and 1, so 6 aggression. Oh, this one goes to 6 too. Oops, there we go. 6 aggression, and then 1 self-efficacy, right there. And then 3 for aggression and 5 for self-efficacy, so right about here. And then 1 for aggression and 6 for self-efficacy, so here. And if I kind of draw a line around this data, whoop, I missed a spot. There we go. Come back here, you. So if I draw kind of like a circle around this data, it's kind of a toss-up for me between strong and moderate. It's kind of spread out, but I can certainly tell it's a negative relationship. But I'm thinking it's probably pretty strong. I mean, this is pretty close to linear. If you look here, these are almost a straight line, and there's just a couple that stray away from it. So I would make the prediction that this would be a strong negative relationship, downward slope, pretty close to linear there. So let's see if that's what we find in our data. Okay, so I'm going to write down all of my formulas. So for my correlation coefficient, that's going to be the sum of products divided by the square root, sum of squares x, times my sum of squares y. Then I need to write down my 3 formulas, right? For sum of products, sum of squares x, and sum of squares y. So my sum of products is equal to the sum of each x times each y minus the sum of all the x's times the sum of all the y's divided by my sample size. Then my sum of squares x, sum of all the squared x scores minus the sum of all the x's squared divided by my sample size, and then my sum of squares y, sum of all my y scores squared minus the sum of y squared divided by my sample size. All right, so I know that I need to find the sum of xy, the sum of x squared, and the sum of y squared, and the sum of x and the sum of y. So to find the sum of x, I can just add these guys together. So 5 plus 1 plus 2 plus 4 plus 6 plus 3 plus 1. And I know that my sum of x is equal to 22. Then for self-efficacy, I add all those scores together, and I know that my sum of y is equal to 23. Now to find this value for my sum of products, I need to take each x times each y. So 5 times 2 is 10, 1 times 5 is 5, 2 times 3 is 6, 4 times 1 is 4, 6 times 1 is 6, 3 times 5 is 15, and 1 times 6 is 6. Add all those guys together, and I get the sum of xy is equal to 52. All right, now let's take all my x values and square them. So 5 times 5, right? I'm just looking here. 5 times 5 is 25. 1 times 1 is 1. 2 times 2 is 4. 4 times 4 is 16. 6 times 6 is 36. 3 times 3 is 9. 1 times 1 is 1. Sum of x squared. Oh, yep, if I add all those together, I get 92. Now we need to take all the y's and square them and add them together. So now we're looking at these guys. So 2 times 2 is 4, 5 times 5 is 25, 3 times 3 is 9, 1 times 1 is 1, 1 times 1 is 1, 5 times 5 is 25, and 6 times 6 is 36. Add those together, and I get a sum of y squared equal to 101. So now I have all of my preliminary calculations completed, and I can start plugging values into my formulas. So let's start with sum of squares y. I'm just going to start from the bottom, work my way up. So when I squared all the y's and added them together, I got 101. And the sum of y is 23. And I know that I'm working with 1, 2, 3, 4, 5, 6, 7 scores. Oh, don't forget your little square here. There we go. So this becomes 101 minus 23 squared is 529. We're going to be dividing that by 7. So this becomes 101 minus 529 divided by 7 is 75.571. And 101 minus 75.571 gives me 25.429. And that is my sum of squares for self-efficacy, or my y variable. Now let's do sum of x squared, or sorry, sum of squares for x. Woo! All right, so sum of x squared, all my x's squared and added together is 92, minus the sum of x, which is 22 squared, divided by my sample size of 7. This becomes 92 minus, so 22 squared gives me 484. We're going to divide that by 7. So this becomes 92 minus, so 484 divided by 7, 69.143. And 92 minus 69.143 gives me 22.857. That's my sum of squares for aggression, or x. Now my sum of products, the covariability of these two. So each x times each y added together is 52 minus, so x, sum of x is 22 times the sum of y, 23, divided by 7. So this becomes 52 minus 22 times 23 gives me 506 divided by 7. And then 52 minus, so 506 divided by 7 is 72.286. And my sum of products is negative 20.286. So yet again, we have a negative correlation. So negative 20.286 divided by the square root. So my sum of squares x times my sum of squares y. So sum of squares x was 22.857. Sum of squares y was 25.429. So this becomes negative 20.286 divided by the square root of, so 22.857 times 25.429 gives me 581.231. So now we solve for that square root. So we've still got our negative 20.286, and the square root of 581.231 gives us 24.109. And our correlation coefficient is negative 0.841. That's our R observed. The observed correlation coefficient in our data. Let's make it all blue and pretty. So then we go back and we say, okay, does that value fall in the critical region? And negative 0.841 is right here. So we will reject the null hypothesis and say, let's see, let me go ahead and just type it in. All right, so reject the null hypothesis. And we'll say that results suggest, you could say this both ways. You could say results suggest that people who have more workplace psychological aggression tend to have significantly lower levels of self-efficacy. I like that. Or you could say there's a significant negative relationship between workplace psychological aggression and self-efficacy. So let's see. is a significant negative correlation between workplace aggression experiences and self-efficacy. Ooh, workplace. And let's make this a little smaller so it actually fits on the screen. Again, you could also say that results suggest that people who have more workplace psychological aggression tend to have significantly lower levels of self-efficacy. So that would be a good plain English way to explain it, right? People who have more workplace aggression experiences tend to have less self-efficacy. And then for this example, a plain English explanation would be that those who tend to work more overtime hours also tend to have less marital satisfaction. All right, so now let's go ahead and figure out R squared for this example. So what is the size of this effect? So R squared equals negative 0.841 squared. Remember, a negative times a negative is never a negative. It's always a positive. And let's see. So negative 0.841 times negative 0.841 is 0.707. And this is a very large effect. And we could say, based on this data, 70.7% of all the differences in self-efficacy can be attributed to the relationship between aggression and self-efficacy. So I like to cover lots of examples and walk you through each step so that you feel prepared to do these things on your own. I really hope that you tried this problem on your own and that you did fairly well. Even if you bombed it, that's okay. That's the whole point of practicing. Nobody expects you to be an expert the first time you do this stuff. What's more important is that you practice, you make mistakes, and you learn from your mistakes. So I hope you now have a pretty thorough understanding of correlation and how to do hypothesis testing with correlation.